All right, looking at class 3.1, we're going to introduce circular motion. So this unit is all about objects that move in circles, not objects that are spinning necessarily, but objects that move in circular paths. So the first thing we need to look at are Newton's first and second laws. Newton's first law is the whole object at rest tends to stay at rest, object in motion tends to stay in motion, unless acted upon by an outside force. It's kind of a convoluted definition. I'm going to simplify it quite a bit right now. A net force. Actually, I'm going to make that even better. A net external force is required to change the velocity Now, velocity, either magnitude and or direction of the center of mass of a system. So let's just read through that again. A net external force is required to change the velocity, magnitude, and or direction, I'm going to emphasize direction, thinking circles, of the center of mass of a system. Newton's second law is the sum of the forces equal the mass times the acceleration. The sum of the external forces on a system equal the mass of a system times the acceleration of the system's center of mass. So here's a quick little video for you to watch. Rather than type that into the address bar, if you have the PDF version of this open on your computer, you can just click on that link. So if we look at this video, it's kind of not a high quality video, but I think it's really good. So we're just going to play it a couple times. So we're going to go back to the beginning really quickly. You should have noticed the ball was moving in a circle. Before the ball moves in a circle, though, think about how it's moving. It's clearly moving in a straight line. Then notice what makes it move in a circular path. Notice the middle of the circle can be like this little silver thing in the floor there. Think about what's making it move in a circular path. And then afterward, notice how it moves in a straight line again. So before entering the circle, the ball travels in a straight line due to Newton's first law. If there's no net external force on the system being the ball's velocity isn't going to change. It's not going to change direction, and it's not going to change magnitude. So it's going to go in a straight line forever. So what does the person in the video do in order to move the ball in a circular path? The person hits it with a hammer, but I'm going to be more broad than that, applies a force toward the middle of the circle. When the person stops hitting the ball, what happens to it? Well, now there is no longer a net external force on the system, so it's going to travel in a straight line at constant speed. Well, it travels at constant velocity, magnitude, and direction. The value of its speed is not changing, and its direction is not changing. Therefore, it's traveling in a straight line. Constant velocity. So use Newton's first law to explain why you must apply a force toward the middle of a circle to keep an object moving in a curved or circular path. A net external force is required to change an object's velocity. In this case, direction. We're not changing the magnitude so much as we're changing the direction. So a net external force is required to change an object's direction. So what do you notice about the direction of the velocity of the ball? What do you notice about the direction of the velocity as the ball moves around its circular path? Well, you should notice that the velocity of the ball, if I were to kind of sketch it, I'll do it in, let's just do it in red, or let's do it in purple. The velocity of the ball is always going tangent to the circle. The magnitude is not changing, but the direction is, therefore the velocity is changing. It is tangent to the circle. Sometimes this is referred to as tangential velocity. So one thing I really want to emphasize today is that if the direction of the velocity changes, then the velocity changes. A lot of people think velocity is only referring to the value, like 10 meters per second, 12 meters per second. No. It also refers to, and spell direction right there, it also refers to the direction. So even if the magnitude doesn't change, if the direction is changing, the velocity is changing. And if the velocity changes, then the object is accelerating. So how can Newton's second law be used to explain that an object moving in a circle must have a net force acting on it? If an object moves in a circle, its velocity is changing. Specifically, its direction. Therefore, it is accelerating. Therefore, the sum of the forces does not equal 0. There has to be a net force acting on it. Now, which way does that net force act? Well, we'll see on the next page. So watch this video. Again, click the link in the PDF version. It does an excellent job of basically explaining what centripetal force is and centripetal acceleration. Not centrifugal, centripetal with a P. So centripetal force is effectively the sum of the forces directed radially, I keep writing the C's, directed radially in or out of the circle. We'll see what that means in a little bit. But basically we have the sum of the forces in the x direction, the sum of the forces in the y direction. When we have an object moving in a circle, the sum of the forces directed in and out of the circle. But basically centripetal force is just like the net force. It does not appear in free body diagrams. Like net force does not appear in free body diagrams. Centripetal force does not appear in free body diagrams. It's just the sum of the circular forces. And centripetal acceleration is the acceleration of an object moving in a circle. So what do you notice about the directions of the velocity of centripetal acceleration? Well, velocity is always tangent to the circle. Centripetal acceleration always points towards the middle, always, always, always. In addition to that, if the acceleration points to the middle, that means that the centripetal force also points to the middle. So AC and FC always point toward middle of circle. So the centripetal acceleration always points to the middle. I can draw more of them in if I like. And the centripetal force also points to the middle. I'm not going to draw as many in, but you can draw in as many as you want. Always points to the middle. So if an object is moving in a curved path, it must have a centripetal force acting on it. But you would never draw centripetal force in a free body diagram. So there has to be what we call an agent of the centripetal force, or a cause of the centripetal force. It could be gravity, it could be tension in a string, it could be friction, it could be the normal force. All those things are agents of the centripetal force. For example, if we look at the top here, these people moving on the roller coaster, if I look at the very top person, notice they have gravity pointing towards the middle of the circle and normal force pointing towards the middle of the circle. So those would both be agents of the centripetal force in that case. Every case can be a little bit more complex or less complex, but that's the very basics of it. You would not draw centripetal force on a free body diagram. So what was the agent of the centripetal force in the bowling ball video we watched? The hammer. Again, pointing towards the middle of the circle. If I whirl a ball around on a string, what's the agent of the centripetal force keeping in that circular path? Tension. And if I really wanted to get into it, if it was a vertical circle, it could also be gravity. But we'll get more into that later. So if I have a car moving around in a circular path and it hits a patch of ice, this is the patch of ice right here. Think about what's going to happen to the car when it hits that patch of ice. So the car goes around, no problem, no problem, no problem, no problem, and it hits this patch of ice. What's going to happen? The car's going to lose control. The car's just going to go this way. So in which direction does the car go? I guess you could say in a straight line tangent to circle. So what was the agent of the centripetal force that helps a car stay in a circular path? Friction. So though you might not recognize it, friction is actually what helps a car when it goes around a circular path. Whenever you, like, if you ever go on an entrance ramp, like the Seaford Oyster Bay Expressway, think about what's helping you stay in that circle. It's the friction between your tires and the road that prevent you from skidding to the outside of the circle. That's why when it's wet or icy, you can't go as fast because you can't get as much friction to keep you in the circle. So famous thought experiment goes something like this. You have the sun, and you have the earth going around the sun. And the path of the earth is something like this. Let's just say it's a perfect circle. If the sun were to disappear, so let's say the earth is going around counterclockwise. If the sun were to disappear, let me just close this for a second so it'll work a little better. Here we are. Okay. If the sun were to disappear, what would the Earth do? The Earth would actually travel in a straight line tangent to the circle. Now, there's actually a PhET simulation we can check out with that one. If we go to so if we go to this PhET gravity in orbit simulation, and we have the Earth going around, notice how the Earth's velocity is always tangent to the circle, and the force of gravity keeping the Earth in that circle is pointed directly towards the middle. Those are at a right angle. If I were to turn gravity off, look at what happens. The Earth goes in a straight line tangent to the circle. Therefore, the agent of the centripetal force that keeps celestial bodies in nearly circular orbits, because they're not perfect circles, is the force of gravity. So if we look at this example here, a moon orbits a planet in a nearly circular orbit of radius r, as shown in the figure. Which of the following free body diagrams could be used to analyze the forces exerted on the moon when it's at the position indicated? So you should be able to eliminate choices C and D, because centripetal force should not appear on a free body diagram. Now we have choices A and B. A lot of people think the answer here is B because they say gravity always points down. That's only true if you're on a planet. Now we're kind of looking at planets from a distance. The force of gravity always acts towards the planet. So in that case, it would actually be A. Now this should kind of make sense because to keep something moving in a circular path, the net force has to be directed towards the middle of the circle. Now this one here, this might be a little confusing. You might say, well, FNet doesn't appear on free body diagrams. It's just asking you to tell us which direction FNet would point. If it's moving in a circular path, FNet has to point towards the middle of the circle, so you know it's not choice D. The centripetal acceleration has to point towards the middle of the circle as well, in the same direction as the net force. So you know it can't be choices C and B. And the tangential velocity points in the direction of motion, so it has to be choice A. And the last one here, if you have a ball going around in a vertical circle, so let's say I have a ball going around with a string or on a string. So here's the middle of the circle, here's the string, here's the ball. And I don't think it really matters which way it's going. Let's pretend this is a perfect circle. Okay, it's a pretty bad circle, but let's pretend it's perfect. Now this is a vertical circle. Whenever you see a vertical circle, vertical circle. You can't ignore the force of gravity. So we're on Earth. So when the ball is at the top, right here, what are the forces acting on the ball? Well, you have tension, and you have the force of gravity. When the ball is at the bottom of the circle, tension points towards the middle. Force of gravity still points down. So you notice how here things are a little bit different. So for this point here, if we were going to do the whole sum of the forces thing, the sum of the forces in this case would be equal to, so into the circle is always positive, would be equal to T1, because they call it T1 at the top, and they call this T2 at the bottom. T1 plus Fg. Down here, the sum of the forces equal, towards the middle of the circle is positive, T2 plus negative Fg. Notice how some of the forces are different as this thing goes around the circle. Now, if you ever try this on your own, it kind of makes sense. If you whip something around slowly in a vertical circle, the amount of tension that is in the string, the amount of force you need to apply as the person holding the string, changes depending on where the ball is in the swing. So the big takeaway is that we have to understand that the centripetal force is the net force that keeps an object moving in a circular path. And just like before, it's comprised of other forces. All right. So we'll get more into examples with this tomorrow, but hopefully this at least gives us an idea of how to get started with circles.